Hello guys. In the last three classes, we talked about the D'Alembert's principle and the Lagrange's equations of motion. So the Lagrange's equation of motion that was derived in the 7th class, that was del L del Q dot, where L is the Lagrangian, ddt of del L del Q dot minus del L del Q is equal to 0. So where L is the Lagrangian, which is kinetic energy minus potential energy, that is one Lagrangian. We can write it like that. But last class we showed that it can be a lot of others. By building, we can build a new kind of Lagrangian by just adding the function like df dt, where f is a function of generalized coordinates and time. So let's call it equation 1. So while deriving this Lagrangian equation, we got a equation like ddt, if you remember correctly, then ddt of del t del qj dot minus del t del qj equal to qj, where qj is the generalized force. Generalized force. Let's call it equation 2. So from there, from this equation, what we assumed, like we assumed this generalized force, these are derivable from a potential. So this qj, it is derivable from a potential, and the potential is v, which we assume like it is velocity independent. So it's depend on q's. It's depend on it depends on q's only. So in that case, we got del v del qj, and we put it here, and because v is velocity independent, this term, this so del v del qj dot, that will be equal to 0. So then we can have like equation 2, we can write like ddt of del t del qj dot minus del t del qj equals to minus del v del qj, which is the generalized force, plus we can write ddt of del v del qj dot, because v is independent, we assume like v is independent of this generalized velocity. So in that case we can write, because this term is anyway 0. So then we take these two terms another side. So then what we got, so it's qj dot t minus v minus del qj t minus v is equal to 0, and this t is equal to 0. So, and this is the Lagrange's equation, where this t minus v is called the Lagrangian. So this is how we derived the Lagrange's equation, if you remember. Now the question is it necessary to assume that v is velocity independent, like v doesn't depend on qj dots? Can we treat the potentials which are like which are dependent of qj dots in this framework, of Lagrangian. So the question is, can we uh, include velocity dependent potentials in the framework of Lagrange's equation of motion? It turns out that yes, we can deal with a special type of velocity dependent potentials. So we can deal with some special type of velocity dependent potential. So what is this special type? So let's look at this equation 3 and equation 1. So if the velocity dependent potential that is let's call it u, which depends on q dot q and q dot, not explicitly dependent in time. So we are only talking about the velocity dependent potentials. In that case, if the velocity dependent potential is this, such that the generalized force derived from this velocity dependent potential, if that is uh, like minus del u del qj, so this term remain, because this minus del v del qj, where v was velocity independent potential. So this term goes with this del t del qj term. This term goes with this del t del qj term, and it gives the Lagrangian here, del L del qj. Okay. So here what we want is qj is such that qj the velocity dependent potential u is such that the general in the, when the generalized force is derived from this u, the velocity dependent potential, then one part it can be written like this term, and there will be another part which will go with this term, and it gives the Lagrangian t minus u. So it's like plus ddt of del u del q j dot. Then from equation 1, what we can have is, then from equation 1, so ddt of del qj dot of t minus del t del qj is equal to qj. Now qj is derived from the velocity dependent potential, then we can get this like this. And if we put take these two terms in, if we take these two terms in this side, then ddt of del qj dot, what we will get is t minus u minus del qj of t minus u equals to 0. And now we can call it this t minus u our Lagrangian, ddt of del qj dot l minus del l del qj equal to 0, where our new Lagrangian is t minus u. So if the velocity dependent potential that gives a generalized force like this, let's call it equation 3, only in that in those cases we can treat them in the framework of uh, this Lagrangian equations of motion. Why we are so bothered about that? Why is it so? Why it is so important? It's because one of the most important potential in physics is the electromagnetic potential energy. So that is velocity dependent. So uh, let's look at that. So let's say E is the electric field. B is the magnetic field. Phi is the electric scalar potential. A is the magnetic vector potential. So such that E can be derived from its potential, which is divergence of phi, and magnetic field that can be derived from this magnetic vector potential, like that. So now the force, the Lorentz force on a charge which is moving with a velocity of v in this electric and where in a space where the electric and magnetic field both are present, the force will be electric force plus q into v cross v magnetic force, which will be q e plus v cross b. So this is the force. So let's call it equation 4. This was equation, so equation 3. Let's call it equation 4. So now we will show that if we take a potential which is a velocity dependent potential like this, q phi, minus q a dot v, then this force can be derived like, so here the q is the charge. Okay, this q is a charge. Let's define it by something else then. Let's define it by E. This q is not generalized potential, generalized coordinates. So then it is a charge. So let's define it by E. Otherwise there will be confusion. So now let's look at this Lagrangian. So in that case, if potential is like this, so we'll show that this potential fits into this framework. This potential gives rise to generalized forces which are like this, and it fits into this framework, into this framework. So the Lagrangian will be T minus U, and T is half m v square minus E phi. So this phi is not a velocity dependent potential. This phi depends on q's, and minus E a dot b. This a also depends on the coordinates. A also depends on the coordinates. But in the potential there is v. So this is the velocity dependent term in this potential expression, in this potential, the expression of u. So now let's see what is the Lagrange's equations of motion in this case. So we will calculate del L, del Q, del Qj. So for here, the generalized coordinates are the XYZ coordinates. So let's look at them in terms of this X coordinate. So we are trying to find the X component of the force. So then del X component of this equation. So the del X will be del X of half m vx v square. V square means v dot v. Okay, v square means v dot v. And what does this v means? V means x dot square. V means x dot I hat plus y dot j hat plus z dot k hat, dot product of, here this dot means derivative dx dt, which is the x component of velocity. We can call it vx also. So here also x dot I hat plus y dot j hat plus z dot k hat. So that we can write it like x dot square plus y dot square plus z dot square, or we can write it we can write x dot like vx square plus y dot as vy, and then that's a square of that, and then vz square. So this is v square. So keep in mind that this vx is basically x dot dx dt. Similarly, vy is dy dt, and vz is dz dt, minus e phi, which will be depend on x, y, z, minus E A A, which will be dependent on x, y, z, and A dot V. So A, it has x component, y component. Let's call them AX, AY, and AZ. And dot product with V, V has its x component is as a VX, y component as VY, z component as VZ. So in that case, this dot product will be AX VX plus AY VY plus AZ uh, VZ. When if we take the derivative with respect to AX, we will get, so there will be no coordinate dependent term in this expression, right? So everything is this is x dot. So x dot, y dot, z dot, these are independent of x, y, z. These are velocities. So in that case, this derivative with respect to del del x in this term, for this term, will be 0. So we will get minus del phi E times del phi del x minus E times uh, del AX del x dx. Okay. Yeah, there will be a plus sign here because U is defined like this. So here there will be a plus sign. So in that case, there will be a plus sign here also. Okay. T minus U, so minus minus plus. In that case, there will be a plus sign here also. Plus del AY del X Vy, because Vy, Vx, and Vz, these are independent of the coordinates x, y, z. Del Az del x, sorry, del x Vz. Okay, so let's call it equation 5. So now let's derive this term del L del x dot, which will simply be del x dot. Let's write it again, of this L, which is this. So half m px square plus by square plus z square minus E phi, which is xyz dependent, plus E ax vx plus ay vy plus az vz. Now we are derivating this whole term with respect to x dot. That means vx. So what we will get is only this term will get the derivative, other will be 0. So then this is m vx, and this term will be 0, derivative of this term will be 0, and derivative of this term will be plus E x, because Vy and Vz, these are independent of x dot Vx, which is x dot is Vx, and this derivative of Vx is 1 with respect to Vx. So we are left with this term, and then if you take the ddt of that del L del x dot, we will get m. So ddt of Vx itself is x dot, so we'll get x double dot, double derivative of x, which is the force, x component of force, plus E dAx dt. Now this dAx dt, this term can be written as so Ax is a function of x, y, z. In that case, this dAx dt can be written as uh, del Ax del x x dot plus del Ax del y y dot plus del Ax del z z dot. So in that case, the Lagrange's equation that we have is, so let's call it equation 6. So in that case, from equation 5 and 6, from 5 and 6, the Lagrange's equation that we have is ddt of del L del x dot minus del L del x equal to 0. And this term, the first term will be from equation 6, which is mx double dot plus e del ax del x x dot plus del ax del y y dot plus del ax del z z dot. And this minus del L del x, so this del L del x term, that will come from this equation 5. So what is del L del x term? It is minus E del phi del x. So that will be plus minus minus plus E del phi del x. And E del phi del x, and there will be a minus sign because there is a minus sign here. Because of that, there will be a minus sign. So minus E this term. Okay. So minus E term is del Ax del x x dot plus del Ay del x x dot or y dot. Let me check. Del Ay del x y dot Vy. Equation 5, it is Vy, so y dot. Y dot plus del Az del x z dot equals to 0. So now these two terms will cancel, this term and this term. So let's see what we are left with. We are left with m x double dot equals to minus E. Let's give it plus. So E minus del phi del x plus del ay del x minus del ax del y dot plus del az del x minus del ax del z dot. So this is what we are getting. Let's call it equation 7. So in that case, what is this minus del phi del x? This is x component of this electric field, Ex. Okay, this is x component of this electric field. So now what is B? The magnetic field. The magnetic field is curl of A, which is defined like uh, I hat, J hat, K hat, del X, del Y, del Z, AX, AY, AZ. So this means I hat del AZ del Y minus del AY del Z my plus J hat. So del AX del Z minus del AZ del X plus K hat del AY del X minus del AX del Y. So this we can call it as Bx, this we can call it as By, Y component of magnetic field, and this we can call it as Bz. So then what is V cross B? V cross B is I hat, J hat, K hat, Vx, Vy, Vz, Bx, By, Bz is equals to I hat Bz, Vy minus By, Vz plus J hat, there will be something, plus K hat, there will be something. So X component of, so V cross B, X component of this will be Bz Vy minus By Vz. Okay, what is By? By is this term, del Ax del Z, del Ax del Z minus del Az del X, del Az del X Vy means Y dot minus minus this term Vy. Sorry. This is Bz. So Bz is this term del Ay del X. Bz is this term. So it's del Ay del X minus del Ax del Y, del Ax del Y, and By is this term. So there is minus By, so we need to interchange these two terms. Then there will be plus. So del Az del X minus del Ax del Z Z Y Z dot. This is the x component of V cross B. So then we know that the Lorentz force F is E times capital E plus V cross B. So then this x component of this Lorentz force, which we term as Fx, will be Ex plus x component of V cross B. And what we got is this x component of electric field, which is minus del phi del x, minus del phi del x, plus this x component of V cross B. From this equation, we can get plus del Ay del x minus del Ax del y. Let's look at the equation. Okay. Y dot plus del Az del x minus del Ax del z. It is z dot. So let's call it equation 8. So now look at this equation, equation 7. What is this? This is same as this x component of this force, generalized total force, right? So look at this term. Look at this term. This term is same as this term here, right? So from equation 7 and from equation 8, from equation 7 and 8, we get Fx is basically equals to Ex plus B cross B x component. So we can generalize that for all three coordinates, which will be F equal to E plus B cross B. So we can derive this equation, this force equation, from this Lagrange's equation of motion, where the potential is velocity dependent and it is defined like minus divergence of plus. So U is defined like this, minus E phi. Oh, it's not a divergence. Divergence of phi is a field. So it will be minus, it is a potential that we are writing. So the potential can be written as E, let's have it, minus E phi plus E A dot V. So velocity dependent potential. So we can treat, it's a very important potential, and we can treat this kind of velocity dependent potential in our framework of Lagrangian equations of motion, because it's U, which is basically it's like in the form of this equation 3. Okay, that's why we can deal with this kind of potentials, velocity dependent potentials, in our Lagrangian framework. Okay, that's all for today. In the next class, we will talk about non-conservative forces. Can we treat them in this framework? So while deriving this Lagrangian equation of motion, we discussed that this potential, this potential that we are writing, so which gets the generalized force. So these generalized forces, or the forces that must be derived from a potential, from a scalar potential. Okay, that's the kind of definition of conservative forces. So what if that this is not the case? This cannot be derived from a potential. What can we do? Can we treat them in this framework? Is there any way? For example, the frictional forces. So those are not derivable from a potential. Those are not conservative force fields. Can we treat them in this framework? So that will be the topic of discussion of our next class. And in the next class, we will also solve some problems. Okay, bye.